Hey class, hope we're doing well. We have new week material that's going to relate strongly to last week's material. So the first thing that I want to bring up though, I have all the formulas here: potential energy, kinetic energy, work, and then our new stuff this week, which is power and efficiency. As well, we're going to kind of play with our work and energy in the sense of friction and kind of energy lost. But we're gaining formulas as we go. You can see that the kinematics formulas and the dynamics formulas are no longer here. There is a formula sheet in the actual file section that is usually updated once every week, once every 2 weeks to kind of reflect where we are. So I just updated it today to include all of these formulas in the actual energy section. So there's an energy section, but in that energy section we talk about work, we talk about power, we talk about all these things, and so it's in that thing. But just making sure that if you are ever, like, I have no idea where all these formulas are, again, there's a formula sheet. It says, there's a folder that says formula sheet there, and it's updated kind of regularly. Okay, let's talk about energy lost, and what I mean by that. Last week we looked at the conservation of energy, in the sense of, like, anytime I have potential energy, if I drop it, the kinetic energy will be the same at the bottom. Now that is true, kind of. If I actually were to drop, let's say, a bowling ball. I don't know why I'm bringing a bowling ball to a very high height, but if let's use a tennis ball. All right, doesn't exactly matter what we use, but a tennis ball. Let's say I'm on top of a mountain and I drop a tennis ball. I have a potential energy, and then at the bottom I have a kinetic energy. The kinetic energy at the bottom won't exactly actually be the same as the potential energy, and that's because there's air resistance, which is a type of force, like a force that is acting against us. So that air, like that air resistance does work in the sense of it changes some energy. It takes some energy away from that problem. Same thing. Let's say there's this massive new slide in Winnipeg. It is a height of 5 meters. Okay, that's pretty high. You think of like the roof of this is like 2.5 meters. So double that. A 5-meter slide would be pretty awesome. Now, if I actually go down a slider that is 5 meters tall, my kinetic energy, my velocity at the bottom won't be the same as the potential energy. That's because, again, there's friction between me and the actual slide. So I lose some energy to friction, or sometimes to heat, or sometimes air resistance, but basically there's some kind of force that is going to take some of that energy away. So that's what I'm going to talk about in this video first, and I'm going to do kind of 2 examples of, like, how do we look at that lost energy and use that. Okay, so these are questions 1 and 3. 1 and 3 from the practice sheet that says, like, conservation of energy with heat and friction. So there you go. All right, let's go through these. I have this up. Nope. There it is. Let's put it up behind me. All right. So we have conservation of energy with heat and friction. It says a 22-kilogram child slides down a ramp. It says at the bottom of 5-meter high ramp. So there was a 5-meter high ramp. So I have mass equals 22 kilograms. I had a height of this slide, which was 5 meters. So I know I can kind of get potential energy right away. It also says the child has a speed of 2.5 meters per second at the bottom of the ramp. It says at the bottom of the ramp. So at the very bottom one, all the potential energy should be kinetic energy. It has a velocity of 2.5 meters per second. It says find the energy lost due to friction. So basically we're going to have to try and find some kind of difference here between the energies that I can find. So let's find my potential energy first, which is just 22 times 5 times 9.8, or 9.8 in the middle. But it doesn't matter. I have a total energy, or potential energy, of 1,078. So potential energy should have been 1,078 joules. The nice thing is I also have a velocity for this kid at the bottom, so I can find my kinetic energy, which is 1/2 22 and v squared, so 2.5 squared. And so when I do this, when I do 2.5 squared times 22 times 1/2, I get something like 68.7 joules. So I started with 1,078 possible, like, potential energy joules. That's how much I should have been transferred. At the end, because they're only going this fast, this is how much energy they have left. They only have 68.7 joules. So we lost a huge amount of energy here. And how much, like, how do I find that? Just basically subtract it, find the difference. So if I go this minus this, like, what was my change in energy? Change in energy, which is kind of like, well, I've heard of change in energy before. Change in energy is work. Yeah, there was work done by friction here. Friction did some work here. So that's my energy lost. Equals 1078 minus 68.7, and so basically it's something like 1009 newtons. So friction did 1009 newtons of energy lost in this scenario. Okay, let's go to question 3, where I have another kind of lost energy part that I can talk about. There's one sneaky little part in there. I shouldn't call it sneaky, but let's talk about it. Question 3, a roller coaster, 500 kilogram roller coaster. So mass equals 500 kilograms. Is moving at 1.2 meters per second at the top. So I have velocity at the top. This is the top. 1.2 meters per second. Okay? The height is 30 meters. Okay? It says of 80 kg. Now this is where I'm going to circle this hugely. 80 kg. That is kilojoules. Kilojoules. Now, if you have to look at your phone what kilojoules is, that's fine. Basically, if I have 1 kilometer, how many meters is it? That's 1,000 meters. So I need 80 times 1,000 because it's kilojoules. So basically, I'm going to convert this right now. Okay, this turns into 80,000 joules lost. Okay, 80,000 joules lost. Okay, to heat, and like you're like, well, how does it just turn into heat? Basically, when you create friction, it creates heat. So heat and friction kind of like to go hand in hand here, okay? So I lost 80,000 joules to heat. What will be the speed of the coaster at the bottom of the hill? All right. Now this is a similar question to what we had last week. There's a potential energy, but as well, this roller coaster already has some kinetic energy at the top as well. So I need to find what's called total energy. So energy total equals potential energy plus kinetic energy. So let's find my potential first. Okay, so I have 50 times 30 times gravity 9.8. So I get potential energy of huge 147,000 joules. Let's find my kinetic energy. My kinetic energy is 1/2 times 500 times 1.2 squared. And I get not nearly as big. The kinetic energy is very small. 360. Kind of an underwhelming number when you think of our potential energy. But that's okay. So what is my total energy? Energy total equals those two together. So 147,360. Okay, so that's my energy total. Technically, again, if I had no friction or no energy lost, I could just take this, plug it in, and find my new velocity at the bottom. But I have lost energy. Okay, it says I lost 80,000 joules or 80 kilojoules to heat. So basically, I'm going to take this and I'm going to minus it from my energy total because that's how much energy I lost. So how much energy I have at the bottom, I'm going to kind of put like energy, and then I'm going to put over here like bottom. How much I have left at the bottom? Well, I have this minus 80,000. And when I do that, I get 67,000. I have a number here somewhere. 67,360. So that's how much energy this actual roller coaster now has at the bottom. And so we can use this to actually figure out the velocity. You can kind of plug this back into my kinetic energy. This is the kinetic energy that it has at the bottom. There's no potential energy left. So it has to all be kinetic energy. And so now I can use this to be equal. So I'm going to use this. I'm going to say this 67,360 equals my 1/2 500 v squared. And so when I isolate for my v, what's my final velocity? So when I kind of like move these over and square root it, I get a final velocity of 16.4 meters per second. Okay, so this is how to kind of look at a question and still using our conservation of energy. Like again, the energy has to go somewhere. But now we're actually factoring in kind of real life scenarios where we're losing it to friction, we're losing it to heat, we're losing it to other things. And so now we can actually use this to kind of figure out more like realistic actual velocities, that kind of stuff. Okay, thanks class. There'll be one more video on our conservation, and then we're going to go into some power and some efficiency for this week as well. All right, let's get this. Thanks so much, class.